Space science is a history of being proven wrong. For every confident prediction about our universe, there seems to be a moment of genuine shock where reality defies the textbooks. This is a countdown of 25 times space scientists were completely shocked, moments where consensus shattered and observations revealed the impossible. By the end, you will have a front-row seat to the discoveries that forced us to rewrite our cosmic story. What happens when a spacecraft drifts off course for no reason, or a star's light vanishes in ways no planet could explain? The universe is far stranger than our models predicted. What do you think it means that our greatest breakthroughs often begin with a moment of stunned silence? The first of these shocks arrived not with a bang, but with a whisper, a persistent nudge that refused to go away. In the late 1980s, as scientists analyzed the trajectories of the Pioneer 10 and 11 spacecraft, they noticed something deeply unsettling. These robotic explorers, having completed their missions to Jupiter and Saturn, were now hurtling toward interstellar space, yet their precise radio signals told a strange story. Both spacecraft were slowing down slightly more than the laws of gravity predicted. It was an almost imperceptible drift, an acceleration toward the Sun equivalent to just 1/10,000,000th of the gravity you feel on Earth. But it was constant and it was unexplained. For decades, this pioneer anomaly haunted physics. Could it be evidence of dark matter tugging at the probes, or perhaps a sign that Einstein's theory of gravity needed revision at the vast scales of the solar system? The implications were staggering, pointing toward a fundamental crack in our cosmic rulebook. The mystery persisted until a team decided to look not at the grand laws of the universe, but at the spacecraft themselves. They built a detailed computer model of Pioneer 10, accounting for every bolt, every instrument, and most importantly, every watt of heat radiating from its nuclear power source. The answer, when it came, was almost mundane. The gentle, steady push of thermal radiation, the simple warmth emitted by the spacecraft's electronics and radioactive decay, was acting like a faint photon break, providing just enough backward pressure to account for the anomaly. The shock wasn't in the solution, but in the lesson. It revealed how easily the subtle, cumulative effects of simple physics could masquerade as revolutionary new laws. It was a humbling reminder that before we invent new physics, we must exhaustively check our own plumbing. While the Pioneer anomaly was a ghost finally explained, another signal from the void offered no such comfort. It arrived on a late summer evening in 1977, a burst of data so extraordinary it compelled a single, stunned word to be scrawled in red pen. The Big Ear radio telescope at Ohio State University was engaged in a quiet, systematic search, listening for any pattern in the cosmic static that might hint at intelligence beyond our world. Then, for 72 seconds, the silence broke. The signal was intense, a narrowband radio beacon perfectly aligned with the hydrogen line, a frequency scientists had long theorized would be a logical calling card for interstellar communication. It rose and fell with the precise rhythm of a celestial object passing through the telescope's fixed gaze. When volunteer astronomer Jerry Amon reviewed the computer printout the next day, he saw the alphanumeric sequence 6EQUJ5. Circling it, he wrote the only comment that fit: "Wow." The shock was instantaneous and profound. Here was a signal that ticked every box for an artificial interstellar transmission. Yet as quickly as it appeared, it vanished. Decades of follow-up observations, using more powerful instruments aimed at the same patch of sky near the constellation Sagittarius, heard only the eternal silence. No repetition, no echo, nothing. That solitary, perfect burst is what makes the wow signal so haunting and so enduring. It is a one-time event, a cosmic shout that we happen to be listening in the right place at the exact right moment. It is the ultimate tease, a mystery that resists both proof and dismissal, forever suspended between possibility and the aching void. It taught scientists a humbling lesson about the sheer, staggering scale of the cosmic ocean they are trying to fish, where even the most promising catch can slip away without a trace. That solitary, perfect burst of the wow signal left scientists with a profound question about what else they might be missing in the quiet. But just 2 decades later, an even deeper shock would arrive, one that did not question whether we are alone, but instead rewrote the ultimate fate of everything. For most of the 20th century, cosmologists operated under a single, grand assumption. The universe began in a big bang and has been expanding ever since. The only question was how that story would end. The collective gravity of all the galaxies, stars, and matter was thought to be acting like a cosmic brake, gradually slowing the expansion. Would it slow to a graceful halt, settle into a static state, or even reverse into a catastrophic big crunch? The goal was to measure the deceleration, to find the number that would tell us our cosmic destiny. 2 independent teams set out to do just that in the 1990s. Using the most reliable cosmic mile markers, they could find a specific type of exploding star called a Type 1, a supernova. These stellar explosions are remarkably consistent, like standard light bulbs across the universe. By measuring how bright they appear from Earth, astronomers can calculate their exact distance. By then measuring how much their light is stretched or redshifted by the expansion of space, they can determine how fast the universe was expanding when that star blew up. The plan was to compare supernovae from different epochs, from the recent past to the ancient universe, to see how much the expansion had slowed over billions of years. What they found was not a slowdown, it was the opposite. The most distant, ancient supernovae were fainter than they should have been. Their light indicated they were farther away than the standard model predicted. The only possible explanation was staggering. The expansion of the universe was not slowing down at all. It was speeding up. Some unknown force was overwhelming gravity itself, pushing galaxies apart at an ever-increasing rate. The scientific community was completely shocked. This was not a minor adjustment. It was a fundamental overturning of the prevailing model of cosmic fate. To explain this repulsive force, physicists had to resurrect an old idea from Einstein, a cosmological constant, and give it a new, mysterious name: dark energy. This invisible something, making up about 68% of the entire cosmos, is now the dominant force shaping our universe's future. The discovery meant the cosmos was not headed for a crunch or a static eternity, but for a cold, lonely, and infinitely expanding dissipation. In one observational result, the comfortable story of a gravitationally bound universe was gone, replaced by a vast, accelerating mystery we are only beginning to fathom. If dark energy revealed a universe accelerating toward an unknown fate, another shock hit much closer to home, rewriting the story of our own celestial companion. For generations, the moon was painted as the ultimate desert, a bone-dry world where astronauts' footprints would lie undisturbed for eons in the perfect vacuum. This belief was so entrenched that when the Apollo crews brought back samples, any trace of moisture found was immediately dismissed as earthly contamination. The lunar surface, baked in unfiltered sunlight and lacking any substantial atmosphere, seemed incapable of holding onto something as volatile as water. That certainty began to crack with a deliberate act of cosmic violence. The LCROSS mission, a purposeful impactor, was sent hurling into a permanently shadowed crater at the moon's south pole in 2009. Scientists expected a plume of dust, a confirmation of the dry regolith they predicted. What the following spacecraft observed as it flew through the ejected cloud was utterly shocking. Spectrometers saw the clear, undeniable signature of water vapor, not just a trace but hundreds of pounds of it mixed with other volatiles. At the same time, data from India's Chandrayaan-1 orbiter had already mapped minerals across the lunar surface that indicated the presence of water molecules bound up in the soil itself. The evidence was now incontrovertible. The moon was not dry. vast reservoirs of water ice lay hidden in the eternal, -400-degree shadows of polar craters, places where sunlight has not touched for billions of years. This was a paradigm shift with staggering implications. Water is the cornerstone of life support, but it is also hydrogen and oxygen, the very components of rocket fuel. The discovery transformed the Moon from a mere destination into a potential gas station and supply depot for deep space exploration. It raised profound questions for astrobiology, suggesting that even airless, seemingly barren worlds can trap and preserve the essential ingredients for life, delivered over eons by comets and solar wind. The shock was not just in finding water, but in realizing how much we had underestimated the dynamic, resource-rich nature of our own cosmic neighborhood. Just as the Moon's hidden water revealed a world less barren than we thought, another nearby planet delivered a shock that cut straight to our deepest cosmic question. The Curiosity rover, rolling across the arid floor of Gale crater on Mars, has been sniffing the thin air for years. Its onboard laboratory, the sample analysis at Mars Instrument, is exquisitely sensitive. On multiple occasions, it has detected a faint but unmistakable signature, methane gas spiking in the local atmosphere. To a planetary scientist, that reading is electrifying and deeply puzzling. On Earth, the vast majority of atmospheric methane is produced by living organisms, from microbes to livestock. On Mars, methane should not exist for long. The planet's thin atmosphere is bathed in ultraviolet sunlight and contains chemical compounds that rapidly break methane apart, giving any molecule a lifespan of just a few hundred years at most. So when Curiosity measures a sudden plume, it implies the gas was released very recently. Something on Mars is producing methane today, not in some ancient fossilized past. This presents two equally shocking possibilities, each a revolution in how we see the red planet. The first is geological. Methane can be created through serpentinization, a process where certain rocks, like olivine, react with water deep underground. If this is the source, it points to a far more geochemically active Mars than we imagined, with vast subterranean reservoirs of liquid water interacting with rock, potentially creating energy-rich environments. The second possibility, the one that sends a genuine thrill through the scientific community, is biological. Certain microbes here on Earth, called methanogens, thrive in dark, subsurface environments, consuming hydrogen and carbon dioxide and exhaling methane as a waste product. The sporadic nature of the plumes, appearing and then vanishing, could hint at a subsurface biosphere periodically venting its presence into the atmosphere. The shock is not a declaration of discovery, but the profound weight of the maybe. It means we can no longer dismiss Mars as an utterly dead world. We must now seriously contend with the possibility that we are not alone, that life, in some simple, tenacious form, might be breathing beneath the rust-colored soil next door. Every new spike on the graph from Gale crater is a heartbeat in the silence, a mystery that refuses to be ignored. While the search for life next door hinges on subtle chemical whispers, the outer solar system presents mysteries of a staggering geometric scale. At Saturn's North Pole, there is a shape that should not exist. When the Voyager probes first glimpsed it in the early 1980s, the image was so bizarre many assumed it was a camera artifact or a temporary trick of the light. But decades later, when the Cassini spacecraft arrived for a long-term study, the shape was not only still there, it was more perfect and more perplexing than anyone could have dreamed. Saturn's North Pole is crowned by a hexagon, a near-perfect six-sided jet stream wider than two Earths placed side by side. This is not a surface feature, but a towering wall of clouds, a hurricane-like vortex with winds screaming at over 300 miles per hour, tracing a precise hexagonal path that has remained locked in place for at least 40 Earth years and likely far longer. The shock for atmospheric scientists was profound. Clouds on planets form swirling ovals and chaotic bands, not immaculate geometric shapes. This was like finding a giant, permanent square drawn by the winds of a terrestrial hurricane. The hexagon's stability is as baffling as its form. While the planet beneath it rotates, this atmospheric pattern maintains its rigid six-sided structure, rotating in sync with Saturn's deep interior like a fixed cosmic gear. Researchers believe the answer lies in the complex physics of fluid dynamics, a phenomenon where different layers and speeds of atmospheric gas can self-organize into stable polygonal shapes under the right conditions. Laboratory experiments using spinning fluids have even reproduced similar, though smaller and temporary, hexagonal patterns. Yet scaling that up to a planetary jet stream that endures for centuries remains an active and humbling puzzle. The Great Hexagon stands as a monumental lesson. It shows us that nature's rulebook contains chapters on elegance and order we have only begun to read, and that some of the solar system's most shocking wonders are not hidden in darkness, but painted in swirling clouds, waiting for us to finally understand the language of their shape. The geometric perfection of Saturn's hexagon shows us order on a planetary scale, but sometimes the universe's greatest shocks come from discovering forms we never even imagined. After its historic flyby of Pluto, the New Horizons spacecraft hurtled deeper into the cold, dark reaches of the Kuiper belt. Its next target was a tiny, distant world known by its nickname, Ultima Thule. Scientists expected a cosmic time capsule, a primordial building block of the solar system preserved in the deep freeze for over 4 billion years. Based on faint observations from Earth, they pictured a rough, potato-shaped object, or perhaps two smaller bodies that had gently merged together in the slow-motion dance of the early solar system. When the first high-resolution images finally arrived in early 2019, the team stared in disbelief. Ultima Thule, officially named Arrokoth, was not a sphere or a snowman. It was a pair of pancakes. Two strikingly flat, pancake-shaped lobes were fused together at a seemingly gentle seam. The larger lobe was flattened like a thick cookie, the smaller one resembled a dented walnut. This was not a shape any leading model of planetary formation had predicted. The prevailing theory, called hierarchical accretion, imagined small, rocky grains violently colliding and sticking over time, building up into lumpy, irregular bodies. Arrokoth's two flat segments joined so neatly suggested a completely different and far more serene origin story. It pointed to a process known as local cloud collapse, where a local pocket of the solar nebula gently coalesced under its own gravity, with two separate clouds forming side by side and then spiraling together in a slow, almost graceful merger. The flatness itself was another profound puzzle. It hinted that the building blocks of planets were not compact balls of rubble, but were perhaps originally collections of smaller, flattened pebbles that had aligned in a disk before coming together. This bizarre, beautiful object forced a complete rethink of our solar system's infancy. It showed that the first steps of planet building were not necessarily chaotic and violent, but could be a calm, orderly waltz in the primordial dark, creating shapes so strange they look more like a child's drawing of a space object than anything science had dared to predict. Arrokoth's serene, pancake-like merger hinted at a gentle cosmic past, but the next shock arrived as a bullet from the void, a visitor with no intention of staying. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at impossible speed. Its trajectory was the first clue to its alien nature. This object was not orbiting our sun. It was passing through, a cosmic tourist on a hyperbolic path that could only mean one thing: it came from another star. Named Oumuamua, Hawaiian for scout from the distant past, it was the first confirmed interstellar object ever observed in our solar system. The initial scramble was to classify it. Was it a comet or an asteroid? Comets, icy bodies from a star's outer reaches, develop glowing comas and tails when warmed by the sun. Asteroids are rocky and inert. Oumuamua showed no coma, no outgassing, no tail. So, an interstellar asteroid, a simple rock from another world. that conclusion lasted only until scientists tracked its path with extreme precision. They discovered Oumuamua was not just coasting under gravity's pull alone. It was exhibiting a slight but definite non-gravitational acceleration, a tiny, consistent push that was speeding it up as it departed. This is textbook comet behavior caused by jets of vaporizing ice creating a natural rocket effect. Yet, pointed observations revealed no dust, no gas, no visible mechanism for this push. The object was dark, reddish, and profoundly inert looking. Then came the shape, deduced from its wild fluctuations in brightness. To account for the extreme dimming and brightening as it tumbled, Oumuamua had to be extraordinarily elongated, perhaps 10 times longer than it was wide, a spinning cosmic cigar or a flattened pancake tumbling end over end. No natural object in our solar system has such proportions. The combined shocks created a perfect storm of mystery, a silent, accelerating, strangely shaped object obeying no familiar category. The scientific community was completely divided. Mainstream hypotheses scrambled for explanations: a fractal dust aggregate, a hydrogen ice iceberg slowly fizzling away invisibly, or a shard of a planet torn apart by its home star. The very strangeness of its properties, however, opened the door to more speculative interpretations, including the unforgettable suggestion from a few scientists that it could be artificial in origin, a piece of alien technology like a light sail. While that remains an extreme minority view, its very mention underscores the depth of the shock. Oumuamua was a data point of one, a messenger that delivered not answers but a profound and humbling lesson. It showed us that the inventory of other star systems is far stranger than our own, built from processes and materials we have yet to dream of, and that the next scout from the deep could rewrite the textbooks all over again. The serene geometry of Arrokoth gave way to a storm of a different order, one of breathtaking power and impossible perfection. When the Juno spacecraft arrived at Jupiter, scientists braced for chaos. The king of planets is a world defined by tempests, its banded atmosphere a churning canvas of the largest storms in the solar system. The poles, they assumed, would be the most chaotic of all, a turbulent mess of colliding jet streams and vortices. What Juno saw when it peered over Jupiter's north and south poles for the first time was not disorder, but art. At the North Pole, 8 colossal cyclones, each wider than the continental United States, were arranged in a precise octagon around a single, massive central storm. At the South Pole, 5 equally gigantic cyclones formed a perfect pentagon, again encircling one central vortex. These were not temporary features. They have remained locked in this stunning geometric configuration, neither merging nor drifting apart for the entire duration of Juno's mission and likely for centuries before. This was ordered chaos on a scale that defied both imagination and every computer model of gas giant atmospheres. On Earth, cyclones are solitary and short-lived, fueled by warm ocean waters and eventually torn apart by wind shear or land. Jupiter has no solid surface and its poles receive very little sunlight, so the energy source for these permanent hurricanes is a profound mystery. Their geometric stability is even more shocking. How do storms that could swallow our entire planet maintain a polite, fixed distance from their neighbors, tracing a polygonal dance that has not faltered? The answer may lie deep within Jupiter, in the way heat rises from the planet's seething interior to interact with the rapid rotation of its atmosphere, creating stable zones of upward and downward motion that cage these monsters in a gravitational and fluid dynamic ballet. This discovery forced a complete revision of what we thought we knew about planetary weather. It revealed that even in the most violent environments, the universe can impose a strange and beautiful order, a lesson written in hurricane winds that will blow for 1,000 human lifetimes. The geometric order of Jupiter's polar storms shows a universe capable of organizing chaos, but at the very heart of our own galaxy, scientists have stumbled upon a different kind of structure, one that seems to defy the very flow of energy itself. For decades, we have pictured the center of the Milky Way as a chaotic engine, a place dominated by a supermassive black hole where matter and energy swirl in a violent dance. It is the last place you would expect to find a barrier, a cosmic wall that says this far and no further. Yet that is precisely what data from the High-Altitude Water Cherenkov Observatory, or HAWK, has revealed. This unique observatory, located on a high mountain in Mexico, does not look at light. Instead, it detects the faint blue flashes created when ultra-high energy gamma rays, the most powerful photons in the universe, slam into the Earth's atmosphere. By mapping the sky in these extreme energies, HAWK created an unprecedented view of our galactic center. What they found was completely unexpected. The distribution of these cosmic rays was not uniform. There was a distinct deficit, a kind of shadow or hole, in the very region surrounding the galactic core. It was as if something was preventing the highest energy particles from entering that central zone. The galaxy's heart seemed to be surrounded by an invisible shield. This great galactic barrier, as researchers call it, acts like a sophisticated filter. It allows lower energy cosmic rays to pass through, but it scatters or blocks the most powerful ones. The shock comes from the sheer scale and specificity of this structure. What natural force could be so discerning? The leading theory points to the tangled web of magnetic fields that permeate the galactic center. These fields, amplified by the intense turbulence and stellar winds from countless stars, could be acting like a maze of cosmic wires. When a high-energy charged particle, like a proton, tries to pass through, these magnetic fields deflect its path, scattering it away or slowing it down until it loses its extreme energy. Another possibility involves the thick soup of turbulent gas clouds that fill the region. The relentless collisions within this dense medium could effectively drain energy from the incoming cosmic rays, like a bullet being slowed by passing through deep water. This discovery forces us to revise our mental image of the galaxy's core. It is not just a chaotic free-for-all. It is a structured environment with its own rules of engagement, where magnetic architecture and turbulent gas create zones of exclusion that shape the flow of the universe's most powerful particles. It is a reminder that even in the most energetic places, the cosmos builds its own walls, not of stone, but of force and field, governing the traffic of light and matter on a scale we are only beginning to perceive. While the galactic core builds walls of force, a single star over 1,000 light-years away taught us that sometimes the strangest barrier is the one we imagine ourselves. The Kepler Space Telescope spent years staring at a patch of sky, watching for the telltale, rhythmic dimming of stars caused by orbiting planets. Its data was a treasure trove of predictable patterns until one star stood out as utterly wrong. Catalogued as KIC 8462852, but now famously known as Tabby's star, it flickered like a dying light bulb in ways that defied all logic. The dips in its brightness were not the gentle, symmetrical shadows of a planet. They were deep, jagged, and completely irregular. At times, the star's light would drop by a staggering 22%, a depth that would require an object far larger than the star itself to cause. Other dips were shallow and chaotic, with no repeating rhythm or schedule. This was not a planet. It was something unprecedented, a star being obscured by a shape that changed from one observation to the next. The scientific community was completely shocked. Kepler had found anomalies before, but nothing this extreme and this inexplicable. The immediate scramble for an explanation launched 1,000 theories, each more fantastic than the last. Could it be a colossal swarm of comets, millions of them, torn from a distant orbit and passing in front of the star? Perhaps it was the debris from a catastrophic planetary collision, a cloud of shattered worlds and dust. The sheer strangeness of the signal even led some scientists to cautiously and controversially raise the possibility of alien megastructures, like a partially built Dyson swarm of energy collecting panels orbiting the star. their irregular shapes creating the bizarre light curve. For years, Tabby's star was the ultimate cosmic mystery box, a Rorschach test in the sky where everyone saw the evidence for their own wildest hypothesis. The resolution, when it began to emerge, was more subtle but no less fascinating. Detailed follow-up observations across multiple wavelengths revealed a critical clue. The star dimmed more in blue light than in red light. That spectral fingerprint pointed decisively to dust. Tiny particles smaller than a grain of smoke scatter blue light more effectively, letting redder light pass through. The culprit, therefore, was likely a vast, uneven cloud of fine dust, perhaps from a disintegrating moon or a family of icy bodies breaking apart, orbiting in a clumpy, elliptical swarm. The shock of Tabby's star was not in finally identifying the dust, but in the journey it forced upon science. It demonstrated how a single, bizarre data point could ignite the imagination and rigorously test our ability to distinguish between the truly revolutionary and the merely unknown. It taught us that the universe is capable of constructing obscurity on a stellar scale, and that sometimes the answer is not a solid wall or a giant structure, but a slowly dissipating veil of cosmic sand. The strange serenity of Arrokoth's formation pointed to a gentle early solar system, but the deeper we journeyed beyond Pluto, the quieter the cosmic story became. After its triumphant flyby, the New Horizons spacecraft did not stop. It pressed onward into the vast, unexplored realm of the Kuiper Belt, a donut-shaped region of icy remnants left over from the solar system's birth. Scientists were eager for a cosmic traffic report. Their models, based on telescope surveys and theories of planetary formation, predicted a certain level of clutter. This far out, they expected to find a diffuse but measurable population of small, dark objects, countless mountain-sized chunks of primordial ice and rock drifting in the deep freeze. The spacecraft's sensitive cameras were tasked with a long-range survey, staring into the darkness ahead to count the faint pinpricks of distant Kuiper Belt objects as they reflected the distant sun's feeble light. The results were not just surprising, they were unsettling. The number of small objects New Horizons detected was far, far lower than anyone had predicted. The space was not empty, but it was strikingly, inexplicably sparse. Where models forecasted a gentle haze of cosmic gravel, the probe saw a stunning lack. This was not a minor discrepancy. It was a fundamental challenge to our narrative of how the outer solar system built itself and settled into its current state. One leading theory had suggested that over billions of years, collisions between larger Kuiper Belt objects would have ground themselves down into a vast population of smaller debris, a predictable outcome of celestial bumper cars. The emptiness New Horizons witnessed suggested a different history. Perhaps the Kuiper Belt's building blocks were originally smaller and less numerous, or maybe the region was efficiently cleared out much earlier in its history by gravitational interactions with the giant planets, which flung most of the small material away into interstellar space before it could collide and fragment further. Another, more intriguing possibility is that the physical properties of the material out there are different. Maybe the icy bodies are less like brittle rock and more like cohesive, fluffy snowballs, so that when they do collide, they stick together or compact rather than shatter into countless pieces. This empty frontier forces a profound revision. It tells us that the processes of accretion and destruction in the cold, dark reaches of our own solar system are not simply scaled-up versions of what happened closer to the Sun. The Kuiper Belt is not a preserved museum of chaos, but a carefully curated gallery, one whose quiet halls hint at a much more orderly and selective clearing process than we ever dared to imagine. The quiet emptiness of the distant Kuiper Belt felt like a cosmic exhale, but closer to home, a single chemical signature ignited a firestorm of controversy. In September 2020, a team of astronomers made an announcement that sent shockwaves through the scientific community. Using two powerful Earth-based telescopes, they had detected the spectral fingerprint of phosphine gas in the temperate cloud decks of Venus. On Earth, phosphine is a molecule that screams life. It is manufactured in significant quantities by anaerobic microbes thriving in oxygen-free environments like swamps, wetlands, and even animal intestines. While trace amounts can be produced by volcanic activity or lightning, the quantity reported in Venus's atmosphere, about 20 parts per billion, was far higher than any known abiotic process on a rocky planet could easily explain. The implication was staggering. Here was a potential biosignature, a hint of life, not on a frozen moon or a distant exoplanet, but in the acidic clouds of our nearest planetary neighbor, a world famously described as a vision of hell. Venus is a crushing, scorching inferno at its surface, with pressures 92 times Earth's and temperatures hot enough to melt lead. Yet high in its atmosphere, about 30 to 40 miles up, exists a layer with Earth-like pressures and temperatures. It is still a profoundly hostile place, with clouds made of concentrated sulfuric acid, but it is the only vaguely habitable niche on the planet. Could floating, acid-resistant microbial life exist there, buoyed by the winds? The scientific world was instantly polarized. The shock was not just in the claim, but in its audacious location. Teams around the globe scrambled to reanalyze the data. Some could not reproduce the signal, suggesting it might have been a misinterpretation of sulfur dioxide, a common Venusian gas. Others defended the original detection. The fierce debate that followed was a masterclass in how science corrects itself in public. It was a raw, real-time examination of extraordinary evidence, with every assumption and data processing step scrutinized. The profound lesson was not whether phosphine was definitively there, but how the mere possibility forced us to completely re-interrogate a world we thought we understood. It challenged us to expand our imagination of where life could tenaciously cling, even in a droplet of acid floating in a toxic sky. This single, contested signal has already changed our cosmic perspective, directly inspiring a new fleet of proposed missions to Venus, designed not just to map its volcanoes, but to explicitly sniff its clouds for the chemistry of life. The search for our cosmic neighbors may begin not in an alien ocean, but in a familiar yet terrifying yellow haze. A world of acid clouds is a difficult place to search for life, but sometimes the universe hides its secrets in plain sight within the most pristine rings of dust. For years, the star Fomalhaut, one of the brightest in our sky, captivated astronomers with its stunning debris disk. Captured in iconic images by the Hubble Space Telescope, this disk was a masterpiece of cosmic architecture. It appeared as a brilliant, needle-sharp ring of icy and rocky material, a perfect belt of construction debris circling the young star. The ring's crisp, defined edges strongly hinted at the gravitational influence of an unseen world, a shepherd planet using its gravity to carve and maintain this celestial fence. Then, in 2008, Hubble seemed to deliver the proof. A tiny, bright point of light was detected moving along the inner edge of the ring. It was announced as Fomalhaut b, the first exoplanet ever directly imaged in visible light. The discovery was a triumph, a validation of both the telescope's power and our theories of planetary formation. But the planet had a problem. It was too bright in visible light and completely dark in infrared, a combination that defied the properties of any known planet. It should have been warmed by its formation and glowing in infrared heat, but it showed none. For years, it was an accepted, if puzzling, member of the exoplanet catalogue. Then the real shock arrived. Astronomers continued to monitor Fomalhaut b, expecting to chart its orderly orbit for decades. Instead, the object began to behave impossibly. It grew fainter in visible light with each observation. More startlingly, it began to lose its compact, point-like shape, spreading out and smearing along its orbital path. By 2020, it had faded into the background glow of the disk, becoming undetectable. This was not a planet's behavior. Planets do not evaporate. The only plausible explanation was as dramatic as it was destructive. Fomalhaut b was never a planet at all. It was the fleeting, brilliant aftermath of a cataclysm. Scientists now believe Hubble had captured the precise moment when two large planetesimals, each perhaps hundreds of miles across, collided in a titanic crash. The impact would have vaporized them, creating an immense, expanding cloud of fine dust and vapor that reflected Fomalhaut's light brilliantly. Over the following years, that cloud simply dissipated, its particles spreading out and drifting on the stellar winds, fading from view. The shock was twofold. First, it meant retracting a landmark discovery, a humbling lesson in the patience required for cosmic detective work. Second, and more profoundly, it provided a real-time glimpse into the violent processes that build planetary systems. We were not seeing a mature world, but a snapshot of the construction site itself, a single, dusty breath from a collision that might one day form a new planet's core. It revealed that even the most pristine, quiet-looking systems are still theaters of occasional, world-shattering violence. While Fomalhaut's phantom planet was a collision caught on film, another discovery arrived as a single, piercing scream from the dark. In 2007, an astronomer named Duncan Lorimer was sifting through old data from the Parkes radio telescope in Australia, searching for the faint, repeating signals of pulsars. What he found instead was a data point that defied all categories, a spike of radio energy so intense and so brief it seemed impossible. Lasting only 5 milliseconds, this burst had traveled for billions of years from a distant galaxy. In that sliver of time, it released more energy than our Sun emits over 80 days. The scientific community was stunned. This was not a signal, it was a detonation, a cosmic flashbulb popping in the radio spectrum with the power of 100 million suns. The sheer scale of the energy, packed into a duration shorter than a camera shutter's click, shattered all expectations. What natural engine could possibly be that powerful, that efficient, and that fleeting? The immediate assumption was that it must be the death cry of something catastrophic, like a neutron star collapsing into a black hole or a magnetar starquake, a one-time event of unimaginable violence. That tidy explanation lasted only until 2012, when the Arecibo telescope detected something even more bewildering. From a small galaxy 3 billion light-years away, a series of bursts erupted, each a perfect replica of that first shocking spike. They were repeating. This was the second, deeper shock. A one-time cataclysm could be filed away as a rare, if spectacular, anomaly. But a repeating source meant this was not a death but a behavior. Something out there was doing this again and again, on a schedule or a whim we could not decipher. It ruled out the simplest, most destructive models and opened a Pandora's box of exotic possibilities. Could it be a highly magnetized neutron star, a pulsar with unimaginable power, processing like a wobbly top and periodically aiming its beam of radiation directly at Earth? Or perhaps it was the result of a cosmic collision, a neutron star orbiting a black hole, with material torn away in periodic, violent eruptions. The repeating nature forced scientists to confront a universe where titanic energies could be tapped and released not in a final act, but as a regular, if unpredictable, performance. Each new fast radio burst that flashes across our telescopes is a reminder of how much we still do not understand about the most extreme physics in the cosmos. A 5-millisecond postcard from a realm where the rules are written in energy we can barely comprehend. The universe's most powerful explosions leave echoes in the dark, but a quieter, structural mystery was brewing right in our own galactic backyard. For decades, cosmologists ran supercomputer simulations of how our Milky Way galaxy should have formed. According to the leading model of cosmic structure, known as the lambda cold dark matter model, large galaxies like ours grew by consuming smaller ones. These simulations consistently delivered a dramatic prediction. Our galaxy should be surrounded by a vast, swarming halo of thousands of small satellite galaxies, ancient clumps of stars and dark matter that never merged into the main disk. Yet when astronomers looked up, they counted only a few dozen. The most famous were the Large and Small Magellanic Clouds, visible to the naked eye in the southern hemisphere, and a handful of other faint dwarfs. Where were the rest? This glaring mismatch between theory and observation was a profound embarrassment for cosmology. It suggested a fundamental flaw in our understanding of how dark matter clumps together or how stars form within those clumps. Were the simulations wrong, or were we simply not seeing the evidence? The shock arrived not with a single discovery, but with a slow, dawning realization as telescope technology advanced. New, sensitive digital sky surveys, like the Sloan Digital Sky Survey, began to peer deeper into the galactic halo. They were not looking for bright, obvious galaxies. They were searching for the faintest possible smudges of light, collections of just a few thousand ancient stars spread over volumes of space as large as the Milky Way's core. One by one, they began to find them, ultra-faint dwarf galaxies. These were not the missing satellites anyone had expected. They were ghostly, diffuse, and incredibly dark. In many cases, they contained so few stars that they were almost transparent, with the light of background galaxies shining right through them. The staggering revelation was their composition. Measurements of their internal motions showed that these feeble stellar wisps were absolutely dominated by dark matter. Their mass was hundreds or even thousands of times greater than the mass of their visible stars. They were essentially invisible dark matter halos that had, by chance, managed to spark a tiny flicker of star formation billions of years ago. This solved the mystery of the missing satellites in the most shocking way possible. The simulations were right about the number of dark matter clumps. Our observations were simply too weak to see the vast majority of them because they had failed to light up with stars. This discovery is now reshaping galaxy formation theory from the ground up. It tells us that the threshold for turning gas into stars in the early universe was far higher than we thought. Something, perhaps the heat from the first generations of stars or the effects of supernova explosions, effectively sterilized most of these small clumps, preventing them from becoming bright galaxies. We are left with a new, humbling picture of our galactic neighborhood. The Milky Way does not sail alone. It is the brilliant capital of a vast, dark empire, surrounded by thousands of nearly invisible dark matter satellites, silent ghosts bearing witness to a time when the universe decided which pockets of darkness would be allowed to shine. The silent, dark matter satellites surrounding our galaxy revealed a universe where most structures never shine, but when a star does dim, it can ignite the wildest speculations. The Kepler Space Telescope, a planet hunter of unprecedented precision, catalogued the rhythmic heartbeats of hundreds of thousands of stars. Its primary mission was to find planets, and it succeeded spectacularly. Yet buried in its torrent of data were a handful of stars whose behavior was so bizarre, so extreme, that they forced astronomers to a shocking crossroads. These stars did not exhibit the clean, periodic dips of an orbiting world. Instead, their light curves were chaotic, with brightness plunging by enormous, irregular amounts, sometimes over 20% for days or weeks at a time. The most famous Tabby star was just the beginning. Kepler found others with similarly extreme and inexplicable dimming patterns. The natural explanations scientists first reached for seemed to strain against the data. A swarm of comets large enough to block that much light would be unimaginably vast and unstable. The debris from a shattered planet would likely disperse or clear on a human timescale, yet some of these stars showed patterns of deep dimming spanning years. In the face of such profound mystery, a radical and thrilling possibility floated into the discourse, not as a claim, but as a testament to the sheer extremity of the observations. Could such immense, structured, and non-repeating obscuration be caused by something built? The concept of a Dyson sphere, a hypothetical swarm of energy-collecting platforms constructed by an advanced civilization to encapsulate a star, moved from science fiction into a brief, serious moment of scientific contemplation. It was a shocking intellectual exercise, less about believing in aliens and more about acknowledging the limits of known astrophysics. The genuine shock was the realization that our catalogue of natural cosmic phenomena might be incomplete, that there could be astrophysical objects or processes, clumps of dust with impossible cohesion, clouds of debris from exotic collisions, so strange we had not yet conceived them. These candidate stars, these cosmic anomalies, served as a powerful catalyst. They pushed astronomers to develop new models, to consider that dust could behave in clumpier, more complex ways around certain stars, or that the disintegration of moons or rings on tilted orbits could create these staggering light curves. The legacy of these moments is not a discovery of intelligence, but a profound expansion of imagination. They remind us that when nature presents a signal that defies all familiar categories, the most responsible scientific response is to honestly confront the gap in our knowledge, and in doing so, sometimes we must briefly entertain the impossible to eventually uncover a new kind of possible. The search for cosmic intelligence forces us to question even the most familiar landscapes, including one we thought we had already mapped into silence. Our own moon has long been presented as the solar system's ultimate museum piece, a geologically dead world whose internal fires cooled billions of years ago. Its surface, scarred by ancient impacts, was believed to be frozen in time, a static record of the solar system's violent youth. That serene picture has now been shattered by a simple, meticulous act of observation. By reanalyzing data from seismometers left by Apollo astronauts and combining it with high-resolution imagery from NASA's a lunar reconnaissance orbiter, scientists made a startling discovery. The moon is shrinking. As its still cooling interior slowly contracts, the brittle lunar crust is breaking, thrusting up sections of itself like the cracked shell of a drying mudflat. These thrust faults appear as stair-step cliffs called lobate scarps, some towering dozens of meters high and extending for miles across the surface. The truly shocking part is that many of these scarps are crisp, sharp, and remarkably free of the pitting from small meteorite impacts that accumulate over eons. This means they are geologically young, likely formed within the last 50 million years, and some may still be active today. The Apollo seismometers, listening in the lunar stillness, recorded shallow tremors, moonquakes that correlate perfectly with the locations of these faults. The moon is not silent. It creaks and groans as it cools. This forces a complete re-evaluation of everything we thought we knew about our companion's inner life. A shrinking, tectonically active moon implies its interior remained hot and partially molten for far longer than our models predicted. It suggests a more complex thermal history and a core that may still be churning with sluggish convection. This isn't just about cracks in the regolith, it's about cracks in our understanding. The moon is no longer a passive backdrop in our sky, but a dynamic world with its own slow, seismic heartbeat, reminding us that even the places we think we know best can still hold the capacity to surprise. The moon's slow, seismic shrinking reminds us that even familiar worlds hold deep secrets, but sometimes the most shocking clues are not seen at all. They are felt in the ghostly pull on distant objects. Far beyond the orbit of Neptune, in the frozen, scattered disk of the Kuiper belt, a handful of icy worlds are behaving strangely. Their elongated orbits are not randomly oriented. Instead, they appear to be clustered as if herded together by an invisible hand. This peculiar alignment was the first clue that sent shockwaves through the field of planetary science. The orbits of these distant objects, like the dwarf planet Sedna and others with perihelia, their closest approach to the Sun, grouped together in a way that defies the gravitational influence of the known giant planets. According to the laws of celestial mechanics, their orbital path should be more randomly scattered. The fact that they are not suggests a massive, unseen force is shepherding them, keeping their orbits in this strange, synchronized configuration. The only plausible explanation proposed by astronomers Konstantin Batygin and Mike Brown in 2016 is the existence of a ninth planet. Not a small, icy body, but a true giant, a world with a mass up to 10 times that of Earth, lurking in the profound darkness of the outer solar system. This hypothetical planet 9, if it exists, would orbit the Sun on a wildly elongated path, taking perhaps 10,000 to 20,000 years to complete a single, slow journey. Its gravitational influence, like a deep, resonant drumbeat felt across billions of miles, would be sculpting the orbits of those distant Kuiper belt objects into the clustered pattern we observe. The shock here is profound because it is a discovery of absence, a planet predicted not by a telescope's image, but by the subtle mathematics of perturbation. It is a reminder that our solar system is not fully mapped, that a world larger than Earth could still be hiding in the vast stretches of our own cosmic backyard, its presence betrayed only by the synchronized dance of tiny, icy specks at the edge of everything we know. The search for this phantom world is now one of astronomy's great quests, a testament to the power of prediction and the humbling possibility that the most familiar star system in the universe still has a giant, dark secret waiting to be found. The search for hidden worlds often hinges on seeing the invisible, but sometimes the universe offers a fleeting glimpse directly into the abyss. Orbiting Jupiter, the moon Europa is a frozen enigma, its surface a cracked labyrinth of ice concealing a global, salty ocean deeper than any on Earth. For scientists hunting for life beyond our planet, this subsurface sea is the ultimate prize, a potentially habitable environment locked away under miles of solid ice. The great challenge has always been access. How could we possibly sample that distant ocean without drilling through a planetary-scale ice sheet? The answer may be that Europa is offering us samples itself. Observations from the Hubble Space Telescope have delivered thrilling, if tentative, evidence of something astonishing. On multiple occasions, Hubble's keen eye has detected what appear to be sporadic, localized plumes of water vapor erupting from the Moon's south polar region, towering over 100 miles into space before falling back as a gentle snow. The implications are staggering. If these plumes are real, they represent a direct conduit from the hidden ocean to the vacuum of space, a natural elevator carrying traces of that alien sea into orbit. A future spacecraft could potentially fly through one of these faint, icy geysers, analyzing its composition without ever touching the surface. It could search for complex organic molecules, salts, and even potential biosignatures, chemical hints of biological processes, all from a safe distance. This possibility generated a wave of cautious optimism that reshaped mission planning overnight. NASA's upcoming Europa Clipper mission, designed to conduct detailed reconnaissance, now carries instruments specifically tuned to sniff out and analyze any such plumes during its dozens of close flybys. The shock lies in the profound shift of perspective. Europa transformed from a sealed vault into a world that might occasionally exhale, offering us a taste of its secrets. It reminds us that the most promising oceans in our solar system may not be the most distant, but the ones that, against all odds, reach out to us. This quiet, dynamic solar system we are still mapping exists within a universe whose fundamental expansion rate we thought we had pinned down. Yet here lies perhaps the most profound and unsettling shock for modern cosmology, a discrepancy so stubborn it threatens the very foundation of our cosmic model. It is called the Hubble tension. At its heart are two exquisitely precise methods for measuring how fast the universe is expanding, a number known as the Hubble constant. The first method looks back to the dawn of time, to the afterglow of the Big Bang itself, the cosmic microwave background. By mapping the subtle wrinkles in this ancient light with missions like Planck, scientists can calculate the ingredients of the early universe, the amounts of dark matter, dark energy, and ordinary matter, and run the cosmic film forward to predict what the expansion rate should be today. That prediction gives a very specific number. The second method works locally, measuring the universe's current expansion directly. Astronomers use cosmic mile markers like Cepheid variable stars and Type 1, a supernova, to gauge distances to nearby galaxies and then measure how fast those galaxies are moving away from us. This is like timing cars on a highway with a radar gun. After decades of refinement, this local measurement also delivers a precise number. Here is the shocking problem. These two numbers, both achieved with incredible precision, do not agree. They are off by a small but significant amount, around 10%. The local universe appears to be expanding faster than the pristine early universe says it should be. This is not a minor statistical fluke. It is a persistent, growing tension that has survived every attempt to explain it away with better data or hidden errors. For scientists, this discrepancy is a deep crisis. It suggests that our standard model of cosmology, the lambda cold dark matter model that has been so successful, might be incomplete or even wrong in some fundamental way. Perhaps dark energy is not constant but evolving, growing stronger over time. Maybe there is an unknown type of neutrino or another exotic particle subtly altering the cosmic recipe. Or it could hint at something even more radical, like a flaw in our understanding of gravity itself. The Hubble tension is a stark reminder that the universe's greatest mysteries are not always hidden in distant anomalies, but can be encoded in the very numbers we use to define reality. A quiet mathematical disagreement that may be the first crack leading us to an entirely new chapter of physics. That tension in our cosmic calculations feels like a distant, abstract puzzle, but one single, nearly massless particle brought the violence of the distant universe into sharp, undeniable focus. On September 22, 2017, a tiny, ghostly messenger slammed into the ice of Antarctica. It was a neutrino, a particle so elusive that trillions pass through your body every second without a single interaction. This one, however, carried an unimaginable punch, packing over 200 tera-electronvolts of energy. It was detected by a vast, cubic-kilometer observatory buried deep in the glacial ice, a network of sensors called IceCube that watches for the faint blue flashes created when such a neutrino very rarely collides with an atom. The detection alone was notable, but the real shock came from what happened next. For the first time ever, IceCube issued a real-time public alert, broadcasting the neutrino's rough arrival direction to telescopes across the globe and in space. Astronomers swung their instruments to that patch of sky, and there they found the culprit. A brilliant flare of gamma rays was erupting from a distant monster known as a blazar, a supermassive black hole at the heart of a galaxy 4 billion light-years away. Its jet of accelerated particles pointed like a cosmic blowtorch directly at Earth. The correlation was perfect and revolutionary. This single ghost particle had been hurled across the universe by one of the most powerful engines known to exist, traveling for billions of years in a perfectly straight line to deliver its message. The achievement marked the dawn of true multi-messenger astronomy, where we no longer just see the universe but can now also feel its particle wind. It confirmed a long-held but unproven theory that cataclysmic events like blazar jets are natural particle accelerators of incomprehensible power, capable of hurling both light and matter to energies far beyond anything we can create on Earth. That one interaction in the deep ice was a Rosetta Stone, finally linking a specific, fleeting particle from the depths of space with the brilliant, explosive light of its catastrophic source, proving we can now read the cosmos in more than one language. While neutrinos and blazars revealed the universe's most violent particle accelerators, a far gentler kind of observation was about to rewrite the rules for an entire class of planets. For years, as we discovered hundreds of hot Jupiter's gas giants orbiting perilously close to their stars, we built a mental picture of these sweltering worlds. They were surely shrouded in perpetual, global cloud decks, their atmospheres a thick, opaque soup of silicate and metal vapors condensing out of the scorching heat. Peering into their chemical makeup seemed like trying to identify the ingredients in a stew by looking at the lid of the pot. Then came WASP 96b. Located about 1,000 light-years away, this planet is the archetype of a hot Jupiter, so close to its sun that a year lasts just 3.5 Earth days. When astronomers pointed the Very Large Telescope in Chile at this system, they used a powerful technique called transmission spectroscopy. They watched as the planet transited, passing in front of its star, and measured which specific wavelengths of starlight were filtered out by the planet's atmosphere. The resulting spectrum was not the bland, muted smear they expected from a cloudy world. It was a pristine, detailed chemical fingerprint. Most strikingly, it contained the complete, textbook-perfect signature of sodium, a pair of deep, clean absorption lines exactly where theory predicted they should be. This was the shock. On a cloudy world, those sharp sodium lines would be blurred and muted, their tops flattened out by the diffuse scattering of light through haze. The fact that they appeared so crisp and clear meant only one thing: the atmosphere of WASP 96b is utterly cloud-free. It is a perfectly transparent window into the depths of an alien gas giant. This discovery overturned assumptions overnight. It proved that not all hot Jupiters are shrouded in uniform gloom. Some possess these remarkably clear skies, allowing starlight to penetrate deep into their atmospheric layers and interact with the gases within, offering a level of detail previously thought impossible. For scientists, it was like switching from a foggy bathroom mirror to a laboratory-grade lens. This pristine window allows them to not just detect elements like sodium, but to precisely measure their abundance and even gauge atmospheric temperature and pressure at different altitudes. WASP 96b became a benchmark, a Rosetta Stone for atmospheric science, proving that sometimes the best view of another world comes not from piercing the clouds, but from finding a place where, against all odds, the clouds never formed at all. That pristine window into a distant gas giant's atmosphere was a triumph of clarity, but the radio sky soon delivered a mystery of profound obscurity. Astronomers surveying the universe with radio telescopes have grown accustomed to cataloging the usual suspects: the brilliant bursts of pulsars, the diffuse glow of distant galaxies, and the circular remnants of ancient supernova. Then, in 2019, a team working with the Australian Square Kilometre Array Pathfinder stumbled upon something that defied every category. Scattered across their deep radio maps were faint, perfect circles of emission, each about the apparent size of a full moon in the sky. They were dubbed odd radio circles, or ORCS, and their existence sent a jolt through the astronomy community. The first and deepest shock was their isolation. These were not the messy, structured shells of a supernova remnant, nor were they the active jets of a known galaxy. They appeared as ghostly rings, empty in their centers, with no visible object at their heart in optical, infrared, or X-ray light. They were phantoms visible only to radio eyes. The initial theories strained to fit them into known boxes. Could they be the spherical shock waves from a gargantuan stellar explosion in a distant galaxy, a supernova remnant on an unimaginable scale? Perhaps they were the throats of enormous black hole jets seen end-on, like looking down the barrel of a cosmic cannon. Or maybe they were the imprint of a galactic wind, a vast outflow of material pushed by star formation across an entire galaxy. Each idea seemed to stretch the limits of known physics to its breaking point. The true shock settled in as more of these circles were discovered. They were not one-off freaks, but representatives of an entirely new class of astronomical object, something previously unimagined and unclassified. Their perfect circular symmetry and sheer size, each one spanning hundreds of thousands of light-years, suggested a phenomenon of immense energy and remarkable uniformity. A single, explosive event or a sustained process that creates a near-perfect spherical wave propagating through the intergalactic medium. Their discovery is a humbling reminder of how much of the radio universe remains unexplored and unexplained. It tells us that the cosmos is still painting with colors our eyes have only just begun to see, and that some of its grandest structures might be hanging in plain sight, waiting for us to finally ask the right question. The ghostly rings of odd radio circles showed us how much remains unseen, but the most unnerving hiding places can be the ones closest to home. Just 1,000 light-years away, a star system visible to the naked eye from the southern hemisphere seemed perfectly ordinary. Catalogued as HR 6819, it was known as a bright, hot blue star with a smaller companion orbiting it every 40 days, a classic binary pair. Then in 2020, a team of astronomers made a shocking announcement after analyzing the system's light with extreme precision. The smaller companion, they concluded, was not a star at all. It was a stellar mass black hole, completely dark and invisible, its presence betrayed only by the subtle gravitational wobble it imposed on its bright partner. If true, this would be the closest known black hole to Earth, a cosmic predator lurking silently in our own galactic neighborhood. The idea was electrifying. Here was a monster hiding in plain sight, not marked by the telltale X-ray glow of actively feeding on a companion star, but dormant and dark, detected solely by its ghostly gravitational pull. It suggested a population of quiet black holes we had simply missed, a hidden network of dark remnants woven between the stars. The shock, however, was quickly followed by intense scrutiny. Other research teams re-examined the same data and proposed a radically different, more mundane explanation. Perhaps HR 6819 was not a simple binary with a black hole, but a triple system. In this model, the bright star was orbited by a close pair of normal stars, their combined motion creating a gravitational signature that perfectly mimicked a single, unseen black hole. This debate is a masterclass in the exquisite difficulty of indirect detection. It highlights the razor's edge between a groundbreaking discovery and a cosmic mirage. The story of HR 6819, unresolved to this day, serves as a profound cautionary tale. It reminds us that the universe is a master of illusion, and that sometimes the most thrilling shadows are cast not by monsters, but by familiar objects arranged in an unfamiliar way. The hunt for the nearest black hole continues, a quiet testament to the fact that even in our own backyard, the line between knowing and imagining is often drawn in starlight and shadow. These 25 moments of shock, from the drifting pioneers to the ghostly circles in the radio sky, are not a collection of random errors. They form a pattern, a map of the frontiers of our own ignorance. Each shock reveals a common truth, the stubborn fallibility of our models. We build elegant frameworks to explain the cosmos, only to watch as a single, bizarre observation, a tumbling interstellar pancake, a hexagon of clouds, a star that winks out by a quarter, shatters the glass. The universe consistently demonstrates a preference for intricate, messy complexity over the simple, orderly systems we so often expect to find. This relentless march of surprises underscores another vital theme, the indispensable role of better tools. The pioneer anomaly was solved not by a grand new theory, but by a more detailed computer model. The missing satellites of the Milky Way were found only when our digital eyes grew sensitive enough to see the faintest stellar ghosts. Each leap in technology, from more powerful telescopes to ice-buried neutrino detectors, doesn't just provide new answers, it reveals deeper, more profound layers of questions we hadn't even thought to ask. Therefore, these shocks must be reframed. They are not failures of science, but its very engine. A moment of stunned silence in a control room, a red pen circling the word "wow" on a printout, a heated debate over a phantom phosphine signal. These are the sounds of progress. They are the friction points where human understanding grinds against the vast, unknown machinery of reality and is forced to adapt. Each shock is a catalyst that pushes us to invent new mathematics, to conceive of new physics, and to ultimately craft a richer, stranger, and more wonderful story of the cosmos we call home. The greatest discovery hidden within all these shocks may be this: the universe is not just out there waiting to be known, it is actively and endlessly teaching us how to see. This pattern of surprise is the true story of our cosmic exploration. Every shock we have encountered, from the phantom pull on a spacecraft to the perfect geometry of a distant storm, has served a single vital purpose. It has broken our comfortable assumptions and forced a fundamental re-evaluation of the principles we thought governed reality. We did not simply add new facts to a ledger, we were compelled to rewrite entire chapters of the cosmic rulebook. Dark energy was not a minor footnote, it became the dominant character in the story of universal fate. The water on the moon transformed a barren museum into a potential interplanetary resource depot. Each moment of stunned silence in a laboratory or control room marked the end of one understanding and the thrilling, uncertain beginning of another. This relentless pressure from the universe itself is what expands human understanding, not in gentle increments, but in great revolutionary leaps. The strength of space science lies not in being right, but in its profound capacity to be proven wrong and to learn from it. As we look ahead, the next generation of tools promises even deeper shocks. The James Webb Space Telescope peers into the atmospheric chemistry of distant worlds. The Vera C. Rubin Observatory will scan the entire sky each night, catching transient events we never knew to look for. Missions are destined for the icy moons of Jupiter and Saturn, ready to taste their plumes and listen for the quakes beneath their frozen crusts. They will not simply confirm what we already suspect, they will inevitably deliver new data that clashes with our current best guesses. They are built for the express purpose of surprising us. So the true call to curiosity is this: stay engaged with this ongoing journey, not for the answers we have already pinned down, but for those next moments of collective shock. The next great discovery is waiting in the data stream, in the unassuming flicker of a star, in the silent trajectory of a probe. It will be the signal that makes no sense, the image that defies explanation, the measurement that contradicts the model. And in that moment of confusion lies the next great leap, the next beautiful, humbling expansion of our place in a universe that is always, always more wonderful than we imagined.